you very much. This presentation is about research undertaken at the University of Valladolid in Spain at the Institute of Sustainable Processes. This research was undertaken as part of my PhD that I performed over the last 6 years together with the group. And that has resulted in several publications and a thesis that I defended last April and was awarded with cum laude. And so I'm very proud to share some of the results. Now, due to limited time, I really would like to explain what is a capillary reactor and show some of the results of some hydrophobic compounds removed in a capillary bioreactor. These compounds different in hydrophobicity and different in biodegradability. So why this research? Now, for odor treatment or gas treatment in general, typical gas contact times of these systems are, for chemical physicals technologies, are several seconds. Now, biofiltration, biofilters, biotrickling filters are easily an order of magnitude larger in contact time. And so really very often especially for good removal of all the odors, gas mass transfer is limiting. Hydrophobic compounds, or the compounds of low concentrations, are a limitation for the microbes to degrade them properly. And so the research is here really about improving the bioavailability, the mass transfer at first for the microbes. Over the years, several studies have been undertaken to overcome mass transfer limitations, and some are very interesting, really work well, but often specific for certain applications or certain types of pollutants, but often makes it very complex and not always good applicable. Now, the area that I wanted to research is capillary reactors. Capillary reactors are structures of small parallel straight channels, round or square, that are divided by a thin wall. And these capillary reactors have gained interest in process intensification over the last couple of decades due to their enhanced mass transfer as well as their improved reaction kinetics. Applications developed for especially the manufacturing of fine chemicals or pharmaceuticals, but also compact heat exchangers. Now, what is really happening is that these channels, only a few millimeters in diameter, both gas and liquid are flowing in the same direction. And if you change that ratio or the conditions, the speed or the liquid itself, you can obtain at a certain area the so-called bubble train or Taylor flow, where alternating gas and liquid gas bubbles and liquid slugs flow through these channels. Now, why is that interesting? That's interesting for two reasons. The first one is that this specific flow regime creates high turbulence. The liquid is recirculating in these slugs. That is because it flows through the channel, and on the side walls there is some resistance, and so you get an internal vortex that creates a very high turbulence. The second is that it has very low, relatively low pressure drop, and this is because of the capillary force. The channels are thin enough that you have capillarity, and we are all familiar with that. If you have, for example, here a porous brick and you place it in a shallow tray of water, over time you see that liquid pulling up, and that's exactly what is happening in these reactors. You see here gas bubbles with liquid slugs in between, and although this vortex you can't see itself, there is a high turbulence inside. This is slow motion. So really the driver here is improve mass transfer, capillary reactors. They can combine good mass transfer, relatively low pressure drop, and studies on these gas liquid capillary bioreactors are very limited. They are either undertaken in a single channel or only for a short period, and in general not focused on hydrophobic gaseous compounds. And so we wanted to understand the fundamentals and see how we can apply these mechanisms for removing hydrophobic compounds. Now, the way this was undertaken is building reactors, in this case glass tubes of about 1.5 meters in length, different internal diameters, but here it's shown as 2.4 millimeters, where gas is introduced at the bottom and it flows through the channel up, and where it is removed again, and then there is a liquid that is recirculated, and they are combined in the bottom reactor to create this so-called segmented flow. This is how these reactors look like. We've built several of them and operated under different conditions. Initially did a lot of abiotic experiments to map the flow regime of this so-called Taylor flow. It's relatively easy actually to obtain that. Done pressure measurements, pressure drops, mass transfer measurements under different conditions, and then also biotic experiments where we looked in the first instance to model hydrophobic compounds, hexane, toluene, and alpha-pinene that we had operating for periods of several months. So here are some of the initial results. Operated at a very short contact time, less than 1 second, and we were able to obtain with these kind of concentrations, inlet concentrations, hexane removals of about 50%, 50-60%, toluene 90%, and pinene around 40%. But very robust, tested against some common upset scenarios, and showed really a good performance. So that was nice, but we wanted to also see if we can enhance that. And silicone oil was here applied So toluene, alpha-pinene, hexene removers were enhanced, and after silicon addition at a contact time of less than 1 second. So really nice results. And biomass here was adhered at the silicon oil phase rather than residing in the water phase. Overall, the treatment of hydrophobic compounds in capillary bioreactors is possible at gas contact times of only a few seconds, with or without silicon oil. And that's in the similar range of conventional chemical physical treatment. Now, another area that we looked at is methane, dilute methane. Approximately 55% of all the anthropogenic methane emissions have concentrations below 5%, and that's the lower exposure limit of methane in air mixtures, and are therefore incompatible for energy recovery or cost-effective abatement. And so we looked at this dilute methane, several 100 to 1000 ppm, and treated them really effectively after some modifications to the liquid. Also after growing microbes that were adapted to the modified liquid. But overall, we obtained, I think, a world record in treating dilute methane in biofilters. It was really possible to have high conversion rates above 200 gram methane per cube per hour over a long period. And more importantly, we did not see any biomass accumulated on the walls of these channels. That was not only observed here with these high concentrations of methane, but also previously in other experiments like with the toluene, hexene and pinene. And so it seems like that these conditions in these reactors, in these channels, create high enough shear stresses for the biological, for the biology not to attach to these walls. And so improving existing designs of bioreactors treating gases with this concept of segmented Taylor flow is promising and can open up new pathways for the abatement of not only polluted air, including odors, but also reducing greenhouse gas emissions, dilute methane, and also applying it for gas biorefineries, where really the bioconversion of gaseous mixtures, for example, biogas or methane into higher value products or biopolymers is really only feasible when this mass transfer is improved. And so with that, there's much more, but I'll leave it up to here, and if there are any questions, please let me know, or if you're interested in any of these publications. Thank you.